What is a chemical bond really? If it is not a tiny invisible rod glued between two atoms? In the energy filament theory, a chemical bond is a shared path that the energy C opens and gradually locks in between atoms. As long as that path exists, the bond exists. When the path collapses, the bond is gone. Picture one atom first. Its outer electrons are not frozen balls but small filament rings running around their preferred loops. Each loop has its own direction and beat. So over time these motions carved a swirling texture around the atom. It's like a patterned wind field around a star. That outer texture is the atom's accent when it speaks to the universe. Now, second atom drifts closer. Long before their nuclei get near each other, their outer wind fields overlap and scan one another, asking a simple question: is there any direction where our spiral textures point the same way and tick at almost the same rhythm? If at some angle the spins and phases line up well, the energy C quietly stretches a new corridor between those matching regions. It's a softer, cheaper lane where an electron can move from one atom to the other with less effort than running only around its home loop. Once that lane exists, one or more electrons begin to oscillate along it, spending time on one side than the other. The more smoothly they run, the clearer the corridor is etched into the C until it becomes a robust shared route. That etched corridor is what we call a bond. When chemists say electrons are shared, it does not mean a bead is parked exactly halfway between two spheres. It means one or more electrons have stopped belonging to just one atom and now keep time along the shared path. They stamp their spiral textures into the energy C on both sides so that the two atoms and the electrons between them behave as one composite structure. Different bond types are just different ways this path is shaped. If the corridor is pulled almost symmetrically so that the easiest place for the electrons to run is near the middle, neither atom gains a clear advantage. We call the result a covalent bond. You can imagine two people holding the ends of a jump rope while the middle of the rope swings evenly between them. If one side's texture is tighter and cheaper, the corridor tilts. Over many oscillations, the electron spends more time on that side. One atom ends up electron poor and positive, the other electron rich and negative. From the outside, we name this an ionic bond, even though underneath it is still one tilted shared path rather than a rigid hook. When many atoms are close enough that each can open paths to many neighbors at once, the picture changes again. Electrons no longer shuttle mainly between two nuclei. They wandered through a whole forest of overlapping corridors, always sliding towards the local downhill slope. On the macroscopic scale, we see this as a metallic electron sea that ties the entire lattice into a single conductive body. A bond breaks whenever the shared path stops being the easiest option for the sea. Heat, strain, or a change in local tension can scramble the rhythm along the corridor so that electrons struggle to stay in phase. They began to miss steps. The moment the energy C finds that letting each electron drop back to its home loops is cheaper than maintaining the corridor, it retracts that path. The electrons retreat into separate atomic orbits, and the bond is gone, leaving two or more atoms free again. The reverse is also true. Whenever two atoms approach in a direction where their outer textures can synchronize, the C will try to open a trial path. If electrons running on that path lower the total effort compared with staying apart, the corridor deepens into a permanent bond, a new molecule is born. So a chemical bond is not a sticky bar wedged between atoms. It is the most economical shared route that the energy Cs can carve between their outer patterns. As long as electrons can keep dancing smoothly along that route, the bond holds. Tap follow, share it on New Physics, Clear Universe.